Griffith. I'm a professor at MIT in biological engineering and mechanical engineering, and I direct two major research initiatives. One, the so-called Human Body on a Chip program to capture human physiology in vitro, and a second emphasis of that is on women's reproductive health. My research for a long time has focused on tissue engineering and more recently on the integration of tissue engineering with this whole new field of systems biology. So what is tissue engineering? When the field started about 3 decades ago, there was tremendous excitement about combining some kind of donor cells, maybe stem cells, with polymers and devices to regrow tissues and organs. And a major focus of my lab has been in trying to regrow livers and bone in patients. Tremendous unmet need. But as we progressed in this research, we realized there were also many, many diseases we didn't understand well, and the only way to really understand them is to study humans, and humans in model systems as well as the human patients. So we shifted our focus of our research into doing tissue engineering in vitro. How can we build complex models of human tissues and organs to study disease, study how drugs work in disease, and better understand all the things that would help us prevent and cure diseases rather than have to replace organs. So our major effort in vitro tissue engineering started with liver. If we could understand liver disease, we could prevent the need for organ transplants. It's very difficult to build a liver because the liver has so many functions in the body. It detoxifies drugs, it's an immune organ, it manages all your metabolism, and so there's many different kinds of cells and it has a lot of blood flow. So to address this, we've combined novel, interesting, exciting biomaterials together with devices. There's an enormous amount of engineering that comes together to build a little micro 3D model of liver that can have even immune responses, metabolic responses that the native liver, many of those features the native liver would have in vivo. So we, over many years, developed this model, and it became so interesting that a company has licensed it and is commercializing it, working with lots of pharmaceutical companies in order to meet their needs. And at MIT, we're not done. We're still developing whole new functionalities in this organ. It's such an important organ in the body for immunology, and that has stimulated us very much to think about connections between the tissue engineering and the systems biology.